Okay, hello. We are going over the back of this worksheet called Parameterization of the Conic sections. This was the homework that was due last week. In the middle of the week it was due last Friday, I guess, but we never went over it, so here it is. Here's number 4. X equals 2 cotan t plus 1. Y equals 5 cosecant t minus 3. Okay, the big idea here, okay, this is going to turn out to be a hyperbola. But, okay, the details are actually maybe a little bit hard. So, let's go. How should we do this? Well, first of all, the cotan graph is hard enough, and because it has asymptotes and there's infinite behavior, and the cosecant graph is also sort of difficult, I think it is worth it to make graphs of these things before we try to do anything else. So, in other words, let's understand x versus t. And, alright, maybe even just a basic graph of cotan. What does cotan look like? Alright, so, I'm a Precalc teacher, so I just know the answer to what cotan t looks like, because I just have this memorized by heart. And the answer is, well, it has period pi, and there are going to be asymptotes at pi, 2 pi, and 0. How do I know this? Well, I guess based on the unit circle. What is the definition of cotan anyway? It's like x over y. And so if you really want to think about what this means on the most basic level, if you sort of didn't know anything, then that's x and that's y. And if cotan t is x over y, then, when y is 0, we're going to have like infinite kind of behavior, because you'll be dividing 1 by 0, since cotan t is x over y, and also when we're up here at pi over 2, cotan is going to be 0. And when we are back at pi, it's also true that the y-coordinate is 0, so we're going to be doing -1 divided by 0, and that's why the cotan is also sort of infinite at pi, and it's just going to repeat every pi, because over here they'll be both positive, here they'll be here the ratio will be negative, here the ratio will be positive again, and here the ratio will be negative. Okay, so what does the actual graph look like? Well, as I just said, near 0, well, in the entire first quadrant, since the x and y coordinates are both positive, the ratio will be positive, and so it's sort of infinite, and then down like this. In the interval from pi over 2 to pi, then the ratio will be negative. Okay, so I just wasted 3 minutes, reteaching you what the graph of cotan looks like. So there it is, and since the period is pi, it's going to look like that. Maybe that was a good use of time, I can't say. How about cosecant t? What does that look like? Well, once again, we can go through the logic of this if we need to, because what is cosecant t? It's cosecant t. Cosecant is kind of 1 over sine, so it's sort of 1 over the y-coordinate. And so once again, whenever the y-coordinate is 0, which happens at pi and 2 pi, then we will get infinite behavior. So that's why the asymptotes are where they are. And then, well, whenever the y-coordinate is positive, which happens between 0 and pi, then cosecant will be positive as well. And halfway through at pi over 2, y is 1. And so that's why you get this point here. But since y is always less than 1, 1 over y will always be more than 1. And so this is just a full-on explanation of the graph of cosecant. Maybe that was kind of overkill. Alright, if you learned all of this, super well in Precalc A, and that's just sitting right there in your brain, then great. If not, you have to kind of conjure this back up again, so hopefully I've helped you do that. So now, what about these? Well, these are just the same thing, but now, a little bit different. So, let's see, I think I have room for this here. Let me graph now Yeah, I suppose I'm going to take this much space for it. Maybe that's too late. So pi, 2 pi, and pi, 2 pi. Okay, so yeah, great. What are we doing? I'm graphing these. What has happened? Well, it's just like regular cotan, except stretched out by a factor of 2 and moved up 1. Therefore, there'll be this point here that's been moved up 1. So that's like pi over 2, and that's 3 pi over 2. And then everything will get stretched out by a factor of 2. So in fact, it will be 2 above, it'll be 2 above and 2 below. So down here at -1, where we should expect the halfway points. So these are like the pi over 4 equivalent points. I won't explain that any further. This is a graph of x versus t. For a given t value, this explains what the x coordinate is doing. And now let's make a graph of 5 cosecant t minus 3. Well, what is that going to look like? 5 cosecant is going to stretch this vertically by a factor of 5. So instead of these being 2 apart from each other, they'll be 10 apart from each other. And then the whole thing is going to be moved down 3. And therefore, we should expect that all the way down here at -8, we're going to have the relative maximum. And this is going to be over here at 2. We're going to have this relative minimum. And so this whole thing has been shifted down 3. Okay, so what is this a picture of? This is a picture of y versus t. Okay, this is quite a lot of preparatory work. I haven't even begun the parametric problem. I have just made very accurate graphs of the x and y coordinates. And I think that's pretty important because the hard part of this parametric problem is kind of understanding these functions well enough to sort of now put them together and to sketch the overall curve. Well, what can I see? Now it's time to maybe look at some restrictions. What are the restrictions on x and y? Well, there are no restrictions on x, right? X is going to use up sort of all real numbers. Of course, this function has period pi. This function has period 2 pi. Therefore, the entire curve is going to repeat every 2 pi. And so, I don't know, somewhere, maybe here or something, I'm going to write that the period equals 2 pi. In other words, every time t cycles through another 2 pi, the curve traced out by this pair of parametric equations is gonna redraw itself again. And therefore, to get a picture of the path traced out by these parametric equations, I need only consider an interval of length 2 pi. And so I'm going to, my sort of plan is to graph this curve on the interval 0 to 2 pi. So specifically the t interval 0 to 2 pi. So I'm going to consider t values on the interval from 0 to 2 pi, and then know that whatever happens on the interval, it's just going to repeat again. Okay, and of course we see that t can't be pi, so that's maybe worth mentioning over here. All right, so good. What do I have to do? Well, I have to investigate the behavior of x and y near places where t is undefined. And since I've now committed to graphing this starting at t equals 0 and ending at t equals 2 pi, I need to look and see what happens as t approaches 0 plus. In other words, I need to ask the question, if t is a little bit more than 0, what are x and y doing? And if t is a little bit less than pi, what are x and y doing? And if t is a little bit more than pi, what are x and y doing? And if t is a little bit less than 2 pi, what are x and y doing? So yeah, for the full correct analysis here, we need to answer all these questions. And I think all these questions are now very easy to answer because we have the graphs sitting right here. Answer, x and y are going to infinity. I could not have done this in my head, or maybe I could have, but I think most people couldn't. Here, x is going to negative infinity, y is going to infinity here. A little bit more than pi, x is going to infinity, y is going to negative infinity, and a little bit less than 2 pi, they're both going to negative infinity. Okay, armed with this knowledge, now I sort of can't go wrong. What's left to do? Eliminate the parameter and graph. How do we eliminate the parameter? Well, here we are going to just use the fact that cotan, well, we're going to use the Pythagorean identity for cotan and cosecant. What is it? You might, not know this or something. So here's my refresher on that fact. There is the sort of basic trigonometric identity involving sine and cosine, which is just applying to it's just the Pythagorean theorem applied to the unit circle, since sine is y and cosine is x. If you then divide through by sine squared on both sides here, then you get 1 plus cosine squared over sine squared is just cotan squared t. And 1 over sine squared is cosecant squared t. So that is a sort of fast way of remembering, once again, if you don't know already, this is kind of a review of the Pythagorean identities for the trig functions. So that's an important thing to know. Alright. If I know that, let me do a couple things in my head because I'm running out of room a little bit. I can just solve for cotan. What is cotan? It's just x minus 1 over 2. And so what we get is 1 plus cotan squared is going to be x minus 1 over 2 squared. And cosecant squared is going to be y plus 3 over 5. Okay, so I think now, if you didn't realize it already, surely now you do, that this is a hyperbola. Specifically, the hyperbola that we get is y plus 3 squared over 25 minus x minus 1 squared over 4 equals 1. Okay, and after doing all that, now I just need to graph this hyperbola. Okay, let's do it. What is this hyperbola? It's going to look like this. Everything has been moved over 1 and down 3. So there's that. I'm a little bit unhappy with how I did this here. Hold on one second. Over 1 and down 3. So 1, 2, 3, 4, 5, 6, 7, 8. So over 1, down 3. So that's the center. And the y-coordinate has been stretched out by a factor of 5, and the x-coordinate has been stretched out by a factor of 2. This is going to be a vertical hyperbola with center at 1, negative 3. And so where are the vertices? They're going to be 5 above the center. So there will be 1 vertex here at 1, comma 2, and there'll be another vertex here at 1, comma negative 8. And then the x-coordinate has been stretched out by a factor of 4, and so I should move, by a factor of 2, so I should move 2 to the left and 2 to the right to make my happy box, which is exactly what I'm going to do now. This problem kind of takes forever. Cha-cha-cha. Okay, and now I can draw the diagonals of my happy box. And now, finally, I can graph my hyperbola. What does it look like? Vertical hyperbola, centered at 1, negative 3, stretched out by a factor of 5 in the y direction, and by a factor of 2 in the x direction. And so the answer is, it looks exactly like this. Okay. What is this point right here? As I said, it is 1, comma 2, and this point is 1, comma negative 8. Okay, now the sort of final thing to do is to annotate this and to explain how this curve gets traced out as t changes from 0 to 2 pi. And for that, I consult my preparatory work, in which I saw that when t is a tiny positive number, both the x and y coordinate will be off at infinity. So that must mean that I am out here at t equals 0 plus. And in fact, we can see that both my x and y coordinates are getting smaller as I move from 0 to pi over 2. And so I'm going down, 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 x and y coordinate getting smaller. And okay, where am I at pi over 2? Well, this is pi over 2 right here. And pi over 2, and that's 3 pi over 2, of course. So when x is pi over 2, when t is pi over 2 rather, x is 1, and y is 2. And so this exact point, 1 comma 2, the vertex of this hyperbola, is where I am at t equals pi over 2. So it's all making sense. Then what happens? Well, now my x-coordinate starts getting smaller, and in fact moves into negative territory, but my y-coordinate starts getting big again, and so I seem to be moving up this branch, and indeed I can see that as t approaches pi minus, my curve is going to be at negative infinity comma infinity, so therefore I shall sort of go off onto this branch as t approaches pi minus. What happens is a teleportation from the top left-hand corner of the top branch to, well, let's see, as t approaches pi plus, I'm going to be at infinity comma negative infinity. And therefore the answer is, possibly surprisingly, that we teleport to this point over here, t equals pi plus. And then, what happens? My x-coordinate's getting smaller, my y-coordinate is getting sort of less negative, bigger, and so I seem to be moving up this thing. Where am I at 3 pi over 2? Answer, I'm at 1 comma negative 8. So this point 1 comma negative 8 happens at t equals 3 pi over 2. Cha-cha-cha-cha. And then finally, as we approach 2 pi minus, my x-coordinate and y-coordinate both go to negative infinity, and so this is going to be t equals 2 pi minus. Okay, we are seemingly done, but of course don't forget that this curve is in fact periodic, and it's going to keep repeating over and over again. So we chose to look at the interval from 0 to 2 pi, but after it completes the interval from 0 to 2 pi, it's then going to start all over again. And so this whole thing is going to teleport once again, sort of back up here, and then going to repeat again every 2 pi. So every 2 pi it's going to go like zoop, zoop, and then teleportation, zoop, zoop, and just repeat again. Alright, so that probably took like 20 minutes or something. Yeah, it's quite a hard problem. It involves a lot of background knowledge. It involves knowing what cot looks like, knowing what cosecant looks like, understanding these curves, being able to graph them, knowing the Pythagorean identities, being able to calculate sort of end behavior, understanding hyperbolas. So it's a great problem. Alright, next. The next problem is sort of even more difficult. It is not straightforward. It's not just something we've done before. It's kind of a new thing that requires a little bit of insight or something. So let's check it out, because I bet some people did, get stuck. Okay. Oh man, this board is getting dirty already. Okay. Great. Well, number 5. What is number 5? Number 5 is the following problem. X equals 2 to the t plus 2 to the negative t, and y equals 2 to the t minus 2 to the negative t. Okay, what can we say about these curves? Alright, well, first of all, perhaps it's worth it to just make a quick graph of 2 to the t, just so we see. What can I say about 2 to the t? Well, it's certainly always positive, and for negative t values it will be less than 1, for positive t values it will be greater than 1 and huge. What does 2 to the negative t look like? Well, it's just going to be reflected across the y-axis, so 2 to the negative t is going to look like this. Okay, so it's certainly true, for example, without even doing much observation that x is going to be positive because, well, I'm adding two things which are always positive. But here, it's maybe sort of less clear what I can say about these two. And, okay, yeah. In fact, you can even say something more about that more than that x is going to be positive. If you want to be sort of very cool or something, you can perform a graphical addition on these two curves. Perhaps this is worth doing. So if this is 2 to the t and this is 2 to the negative t, are we smart enough to sort of add them kind of graphically? I think we can kind of do that. I mean, unfortunately, these graphs are going to be, sort of not that accurate. But anyway, it's going to be way up here. When is this thing going to be a minimum? I say that the smallest it's ever going to be is here at 2. So I actually think, this is not a proof, but I think that x actually has to be greater than or equal to 2. Because basically we're adding kind of like an exponential to something very, very tiny. And here we're adding an exponential to something very, very tiny. And so the smallest the sum ever is when they're both 1. Anyway, hopefully that will just kind of come out later. And y, I'm not even sure what to say about y. It's not obvious what the restrictions here are at all. Okay, so lacking kind of any real intuition about what 2 to the t minus 2 to the negative t looks like, perhaps I should at least do end behavior. So there are no restrictions because I can take 2 to the anything. So all t values are going to be fine. So I don't know, let's just look at what happens as t approaches infinity, and then let's look at what happens as t approaches negative infinity, and that's all we can do, and then we're just going to get started with the problem. Well, let's see. I can kind of just see already from my graphs that x, this is going to become huge. And I'm adding something like infinite to something very, very tiny. And so x is definitely going to infinity. And what can I say about y? Well, I think the same thing, right? Because now, yeah, if t is very, very huge, then this is going to infinity, and I'm subtracting something which is very, very tiny, so that's also going to infinity. But now, as t approaches negative infinity, what's happening? Well, 2 to the negative infinity is very, very tiny, so I'm adding something very, very tiny to something that is now going to be huge. So x is going to go to infinity, and how about y? Well, now 2 to the negative a million is going to be basically 0, but 2 to the negative a million is going to be huge. So y is going to negative infinity. That was not the greatest explanation. What I'm really doing here, I suppose, is I'm plugging in like negative 1,000. And I'm basically saying, all right, what happens when you plug negative 1,000 into this formula? Well, 2 to the negative 1,000 is like 1 over 2 to the 1,000. So that's just a microscopically tiny positive number. So that's like irrelevant. So now let's look at this. Well, if you plug negative 1,000 in for t, then it's 2 to the negative 1,000. Well, that's 2 to the 1,000. That's a huge negative number. I guess that was a pretty good explanation. Alright, so I've run out of background work to do. Now I just gotta get started. And I have to eliminate the parameter. And it's very not obvious how to eliminate the parameter here. But there is one thing that is like extremely tempting to do with these two equations. And you had to kind of think to do this. So I don't know what to tell you, but this is the fastest way to do this. One of the things you have to think of to do this problem is to say, okay, look, these two equations are so similar to each other. My goal is to get rid of t. First of all, let me just kind of add these two equations. If I add these two equations, what do I get? Well, I get that x plus y is 2 to the t plus 2 to the t, right? So in other words, 2 times 2 to the t. Okay, great. That's kind of interesting. Well, what about another idea is to subtract these two equations from each other. So, alright, once again, you had to kind of think to do this, but these equations are also kind of begging to be subtracted, because when you subtract, you know, these two guys cancel. So if you subtract, then you get x minus y equals 2 to the negative t minus negative 2 to the negative t. So that's 2 times 2 to the negative t. Okay, now my goal is still to get rid of t. Alright, well, there are many things that one could do now. For example, if you didn't see what to do on the next step, you might try some way to kind of combine these two equations together somehow to produce some equation that has no t's in it. That's only in terms of x and y. That's the whole goal, right? Well, one thing you might conceivably do here is you might write this as x minus y equals, what is 2 to the negative t anyway? It's just 1 over 2 to the t. And if that's your idea, then I think I got something now, right? Because then I can solve for 2 to the t. What is 2 to the t? It's 2 over x minus y. And if 2 to the t is 2 over x minus y, then can't I just take that and stick it in right here, and then I'll have no more t's. And yeah, you can totally do that. And if you do that, you're going to get the right answer. I'll just say that the absolute smoothest thing to do is to just take these two equations in the green boxes and just multiply them together. If you multiply them together, what do you get? You get that x plus y times x minus y equals 2 times 2 to the t times 2 times 2 to the negative t. So, if you're sort of very good at algebra, or if you just got lucky and saw to do this, of course 2 to the t times 2 to the negative t, these are just reciprocals. These multiply to be 1, because this just means 1 over 2 to the t. And so, quite quickly, you find that the answer is just x squared minus y squared equals 4. Whoa. Therefore, it seems that this is actually just a hyperbola. And it really is just a hyperbola. It's, I guess if I want to put it in standard form, I should divide. So that's x squared over 4 minus y squared over 4 equals 1. I guess we like that formulation a little bit better. Well, okay, what is this? It's a square hyperbola centered at the origin, stretched out by 2 in both directions, and cha-cha-cha-cha-cha, cha-cha-cha-cha-cha, and I will draw the asymptotes, and okay, now I'm ready to graph my hyperbola. It's going to be horizontal. There's going to be a vertex here, and now I sort of reach for my observations that I made at the very beginning, which is that x has to be positive. So in fact, it seems that only the right branch of this hyperbola is happening. And there it is. And yeah, indeed we were right that x did have to be greater than or equal to negative 2, to 2. And okay, I'm pretty much done. Let's just annotate this a little bit. Where do I begin at time negative infinity? Answer at infinity comma negative infinity. So this is my t equals negative infinity. And I must be kind of going up this way. And as t approaches infinity, I'm over here. And I would kind of like a little bit more, a few more points just to kind of feel a little bit better about myself. For example, when t is 0, well, anything to the 0 is 1. So when t is 0, I just get 2 comma 1 minus 1 is 0. And so here is where I will be at t equals 0 at the point 2 comma 0. I suppose we could get, more points if we really wanted. For example, suppose you plugged in 1, maybe. Then you would get 2 plus 2 to the negative 1 is just a half, so you'd get 2.5. And here you'd get 2 minus a half. So you'd get, 5 halves comma 3 halves. So if you did want a little bit more accuracy, well, there it is. 5 halves comma 3 halves, and that point occurs at t equals 1. And I suppose if you plugged in t equals -1, you'd get a nice point also. But that seems good enough for me. Okay, woo! That was number 5. That's pretty hard. Let's do number 6. Number 6 is more straightforward. This is kind of not anything new, but it doesn't make it easy. All right. Yeah. Good. What was number 6? Number 6 said x equals 8 cosine t plus 2 and y equals 6 sine squared t minus 1. Okay, let's go. What can we say about this? Well, first of all, cosine t is always between -1 and 1. So 8 cosine t will always be between -8 and 8. So 8 cosine t plus 2 will always be between -6 and 10. So this x coordinate, whatever else happens, is always going to be between -6 and 10. Alright, great. Next, what can I say about y? Well, sine t is always between -1 and 1. So sine squared t is always going to be between 0 and 1. So 6 sine squared t is always going to be between 0 and 6. And so 6 sine squared t minus 1 is always going to be between -1 and 5. So y is going to be between -1 and 5. Perhaps you could have done some of that just in your head. But anyway, there it is. So, of course, these curves are periodic. This this 8 cosine t plus 2 is going to have period 2 pi. This sine squared, I happen to know, and we've talked about many times, will have period pi. So in fact, if the x-coordinate is repeating every 2 pi and the y-coordinate is repeating every pi, then the entire curve will repeat every 2 pi. So I'm just going to choose to graph this, on the interval from 0 to 2 pi, and then just kind of know that it repeats. Okay, great. What kind of a shape is this going to be? Well, there's no end behavior to calculate here because it's periodic. So I think we're just going to go right into eliminating the parameter. Alright, how should we eliminate the parameter? Well, here, to me, there's kind of an obvious thing to do, which is to express sine squared in terms of cosine. So, I will start with the y equals equation. Y is 6 sine squared t minus 1, and in place of sine squared, I will write 1 minus cosine squared. And why is that good? Because I can tell you what cosine is. What is cosine? It's x minus 2 over 8. So this is going to be x minus 2 over 8 quantity squared. So I think that was pretty straightforward. I'm just using the Pythagorean relationship between sine and cosine. Alright, well, I've already eliminated the parameter. Now it's just a matter of making this a little bit more clear. So let's do that. Let's see, if I distribute this through, I get 6 minus, I guess I want to simplify this. I don't even know. Sure, so that's 6 over 64 times x minus 2 squared, and then there's also just this minus 1. So what do we get? We get y equals -3 over 32 x minus 2 squared plus 5. And, okay, I suppose I could sort of do more things. with that, but that's fine with me. This is just a parabola. This is just a y equals parabola, so just a regular old parabola. And what do I want to say about it? Well, when x is, it has been shifted over 2 up 5. So over 2 up 1, 2, 3, 4, 5. And here is my point 2, 5. That's going to be the vertex of the parabola. And let's see, I don't even really want to do this, but I guess I should get another point. Yikes. I don't really want to. So maybe I'll just kind of pause for a minute. Let's plot some points using t. So let's see, I'm going to just do this part in my head. When t equals 0, cosine 0 is 1. So that gives me 8 plus 2, that gives me 10. So when t is 0, I get 10 comma, but sine t is 0, so 10 comma negative 1. So, alright, way out here at 10 comma negative 1, I'm going to have a point. That is t equals 0, 10 comma negative 1. And, well, what next? Maybe now I shall plug in pi over 2. If I plug in pi over 2, cosine pi over 2 is 0, so I get 2 comma 5. So it's at here when I am at pi over 2. What about 3 pi over 2? Cosine 3 pi over 2, pi now I guess. When you plug in pi for t, cosine of pi is negative 1, so that's negative 8 and 2, so that's negative 6, negative 1. So, bum bum. So negative 6, negative 1 over here. And in fact, perhaps it was worth mentioning that all this work I did over here is exactly coming into play, right? Because I already knew that my whole shape was going to occur inside of a box bounded between negative 6 and 10 in the x direction, and negative 1 and 5 in the y direction. And so I sort of already knew that this whole shape is going to be happening inside this rectangle. And so indeed, because of this algebraic relationship, I know it's a parabola. So this is going to be a truncated parabola. And therefore, it's actually just entirely expected that it's going to look exactly like this. So at t equals 3 pi over 2, this is t equals pi, I mean to say. That's how I got that point, negative 6, negative 1. When t is 3 pi over 2, cosine 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1, but when you square it, you get 1, so that becomes 6 minus 1 is 5. In other words, I'm back up at the point 2 comma 5 when t equals 3 pi over 2 as well. And therefore, I now know that this is going to look like this. So what is this thing doing? It's starting here at t equals 0. It's going up here. By the time I get to pi over 2, I'm here. Then back here for pi. Then back here for 3 pi over 2. Then back here for 2 pi. And it's just going to repeat that back and forth forever. Okay. Good job. That's it. Goodbye.